Hi, and welcome to 12.2 Current and Magnetism. This topic is all about the relationship between the electric field and the magnetic field. And in this homework activity, it's a bunch of multiple choice questions that if you don't know the right hand rules, a lot of them don't make a whole lot of sense. So let me show you the right hand rules. They're kind of like ways to remember how the electric field and the magnetic field are related to one another. So here are the rules real quick. This is the first rule. You basically, if it's current in a wire, so if there's a wire and current going through the wire, the moving electrons actually create a magnetic field. So how do you know where's north and where's south? What direction is the field? That's dictated by where the current is. So as you can see in the diagram, you put your thumb in the direction of conventional current. So not where the electrons are flowing, but where the current is going. Remember we said in Unit 11, the conventional current is where a positive charge would go, even though we know in the back of our minds the negative electrons are the things that are moving. So your thumb goes in the direction of conventional current, where a positive charge would go if it was moving in this wire. And your fingers wrap around the wire in the direction of the magnetic field. Like your fingertips are where you would make the arrowhead, as you could see in the diagram. So you could practice this with your pen or pencil. Point, so your pen or pencil has a pointy side to it. Make that pointy side the direction of the current. So in this, if you're going to mock this diagram, make your pencil sticking up, put your thumb along with it, and then wrap your fingers around the pencil. Unfortunately, these are kind of hard to show with just PowerPoint slides. It's better to be in the classroom and like we'll all do it together. But this is what we got right now. So that's kind of right hand rule number one. And the questions in the activity kind of go in order. So it's kind of weird. Yeah, you could create a magnetic field just by having current in a wire. And then us humans, we're pretty clever sometimes. And we're like, okay, if the wire is making a magnetic field, how can I like make a strong magnet out of this? Well, people figured out if you wrap the wire around in a coil, the magnetic field kind of like builds up on itself. So that's where right hand rule number 2 comes in, is anywhere you see like a coil of wire like this, it's actually known as a solenoid, that you could use right hand rule number 2. And these are useful. They're like electromagnets. So you just flip a switch to turn on the current, and all of a sudden you have a magnet, and then you turn off the switch and the magnetic field stops. So you could see there's a lot of useful applications for this. This one's a little bit different. So you could see in the bottom left-hand boxes there, your thumb is the current in right hand rule number 1, but in right hand rule number 2, your fingers become where the current is. And if you look at the diagram, I don't know, can I draw on this PowerPoint slide? Yes, I can. So the direction of the wire is super important. Do you see how the wire is in front of the little bar right here? So look at the bar and then look at where the current is going. The current is going, you have to visualize the wire wrapping this way. And then on this side, it wraps behind it like this. And you basically want to, you could use your pencil or pen again as like the thing you're wrapping your fingers around. You wrap it in front over here, in front, and then see how the person's fingers are behind it like that. So their fingers are going in the direction of the current now. And your thumb points towards north. So the magnetic field goes out of north and into south. I'll show that real quick. So once you have your fingers wrapping in the direction of the current of the wire, your thumb is pointing this way, and it goes out of north into south, out of north into south. And it ends up looking just like the diagram, out of north into south, for a bar magnet. So this is a very poorly drawn diagram, but the idea is that you are creating a bar magnet just by having current in this wire, and your thumb is pointing towards north because your thumb points in the direction of the field, so it's going out of north and into south. Okay, so that's kind of how right hand rule number 2 works. Right hand rule number 3 is even weirder. So I don't know if you could tell in this diagram, but you have three vectors. One is where your thumb is. One is the direction of your index finger. So it's like you're pointing at somebody with your thumb up. And then this is trying to show you stick your middle finger out in the third direction. The dot means out of the paper. So it's kind of like a little physics hand signal that you give each other. You stick your thumb straight up, point your index finger out, and then 90 degrees from that, your middle finger sticks out kind of weirdly. All right. So that's the three directions. That's the X direction, the Y direction, and the Z direction. We're talking about 3 dimensions here. And you could use this right-hand rule to show the direction of these vectors here. So let's talk about what each one represents. So for this one, there's a pre-existing magnetic field. It's not like the other ones where the wire creates the magnetic field. So yeah, the wire's creating a magnetic field, sure. But what if you already have a magnetic field and then there's a current? They're going to interfere with each other and then you wind up with a force. So your middle finger is pointing in the direction of this pre-existing magnetic field. So towards the end of the activity, you'll see there's a pre-existing magnetic field, and then there's an additional current, so there's some kind of current somewhere. So you put your middle finger in the direction of the magnetic field, your index finger points in the direction of this new current, and then your thumb will point in the direction of a force that's going to be felt. And if you look through this PowerPoint that I have here, this is a link to a pretty cool video. And the idea is this guy has these are magnets, so there's a magnetic field. There's current in this wire, so there's your current. So a pre-existing magnetic field, there's current in the wire, and then a force is felt, and it's cool. The wire ends up spinning because of this force. So it's kind of like a cool demonstration that you could do right in the classroom. And that's that. Now there's an alternative some people like this way, and you might see it in your textbook. It's still talking about 1, 2, 3 directions. All right, just like this was 3 directions, but now it's like defining the things differently. So I'll let you take a look at that. I don't want to confuse you by talking about it, because it's like basically the same thing, but you could see that they're defining this is all completely different. It's just a different way to do it. You have 3 different directions, X, Y, and Z. All right, so now that we kind of know the rules, I'll do my best to explain the activity here. So for number 1 and 2, it's kind of just asking, do you know what causes a magnetic field? And we should know by now that a moving electric field creates a magnetic field. So number 1 says magnetic fields are produced by particles that are, you need to be a charged particle and you need to be moving. So definitely not neutral and definitely not stationary. You need to be moving and charged to create a magnetic field, like an electron. An electron is charged. If it gets going, then there's a magnetic field around it. And that's what we're talking about with current in a wire. Moving electrons, moving charged particles create a magnetic field. Number 2, which type of field is present near a moving electric charge? So because it's an electric charge, it definitely has an electric field. So that's cool. And it's moving. So it's a moving electric charge. So there's a magnetic field too. So that's why there's, both an electric field because it's an electric charge and a magnetic field because that charge is moving. Number 3, that's right-hand rule number 1. So take a look back at right-hand rule number 1. We're going to point our thumb in the direction of conventional current, and our fingers are going to wrap around in the direction of the magnetic field. So it's kind of hard to describe without looking at the picture, so I'll show the picture here. All right, so the X's mean into the page. Oh, it says right here. Magnetic flux line into the page. The magnetic flux line is out of the page. You could think of it like an arrow. So if we're going to the right, all right, what does this person see? This person sees the dot of the arrow coming at them. So when you see the dots, picture, oh, this is like a lot of arrows coming right at me. And this person who fired the arrow, standing over here, they see the feathers. And if you look at this, it's like feathers moving away from you. So here, it's like all feathers moving away from you. So that's kind of, again, I kind of mentioned in right hand rule number 3, we have to think three-dimensionally now. So that's why we have this weird into the page, out of the page idea. So the question reads, which diagram best represents the magnetic field around a straight wire in which electrons are flowing from left to right? And it even gives you a hint. It says, remember, conventional current runs opposite the direction of electron flow. And this just adds a whole other confusing aspect to this. Because remember, our thumb should be pointing in the direction of conventional current, but the question tells you what direction electrons are flowing. So you have to remember that electrons flow opposite the direction of conventional current. So I guess we should write in the direction of I. That way I could show you, you could like point your thumb. We want our thumb to point in the direction of the conventional current. So I'm going to use this color here. Conventional current flows out of positive and into negative. So this is I. Out of positive into negative. As I do this, point your thumb in the direction of the current. So hopefully your thumb is pointing to the left. And if your thumb is pointing to the left and you wrap your fingers around, on top, are your fingers wrapping into the screen? And then on the bottom, as it wraps around the bottom, they're pointing at you, right? So they're coming out of the screen at that point. So we want a choice where the top is going into the screen, the magnetic field lines are going into the screen, and on the bottom, it goes out of the screen, and that's going to be choice A. Okay. I know it's a little tricky. It's hard to do without seeing it, but hopefully you're following along. It's not a huge deal. These are all questions basically from like the 1980s. They don't really ask it on the New York State Regents, but it's fun to do in class. And I like right-hand rules. We've done calculations in this class. We've looked at graph, but actually using a right-hand rule, it's kind of like a weird and quirky, fun thing. So, number 4, the diagram below represents the magnetic field around point P. Okay, so now they're telling you the direction of the field, and they're asking what is the direction of electron flow. Again, this is from the 1980s. And just so you know, if it's asking for the electron flow, technically you could use your left hand and your thumb points in the direction of the electron flow. And that's going to give you the opposite of the right hand, where your thumb points in the direction of conventional current. But I like to stick with the right hand rules, and I like to remind you that electron flow is opposite conventional current. It's kind of like a good review. But let's see. So we want to wrap our fingers. Everybody practice wrapping your fingers. Picture like wrapping your fingers around this thing right here. Okay, so your fingers are wrapping around. Your finger goes into the screen here and out of the screen over here. What direction does your thumb have to point? Hopefully you said your thumb is pointing up. So this is the direction of conventional current, which means that electrons are flowing opposite that. So they're flowing down from B to A. I covered up where it said B. But from B to A, okay, that's the direction of electron flow. All right, so now we have a wrapped up wire. And as soon as I see that, I think about right-hand rule number 2. And now we have to flip. Remember I said before your thumb was the direction of the current. Now your fingers are the direction of the current. And you have to, it's important to see in the diagram, is it in front? Am I wrapping my fingers in front of it, or is it behind? That's an important, you'll get the answer wrong if you don't look at that. It's an important thing, even though it's so subtle. Look how subtle that is. I'm looking here and here. On the left, right here, the wire is in front of that nail, and then it wraps behind it here. And that's going to help us determine what direction to wrap our fingers in the direction of conventional current. Let's read the problem. It says the diagram below shows an electromagnet made from a nail, a coil, insulated wire, and a battery. The south pole of the electromagnet is located closest to point A, B, C, or D. So it's going to be D or B. Those are where the poles are. But where's the south pole? Okay. So the first thing is to identify the direction of the conventional current. So current flows out of positive and into negative. So we want our fingers to wrap in that direction. Now I'm looking over here. My finger is going to go behind this and wrap in front of it like that. Okay, so maybe practice with your pen or pencil that you have. So wrap your fingers behind your pen or pencil, and your thumb, hopefully your thumb is pointing towards point B. So point B is where our thumb is pointing. Your thumb is pointing this way, and that's actually where north is. We said that's where north, it goes out of north and into south. That's the direction of the magnetic field, out of north and into south. And we're basically making a little bar magnet. These are the magnetic field lines for a bar magnet, out of north into south. So if north is on the right side, that's where your thumb is pointing. That means south must be on the left side, and south is where point D is. Tricky stuff, tricky stuff. Again, you really have to look at like the wire. Is the wire going in front of or behind? And what does that mean for how we're going to wrap our fingers and what direction our thumb is pointing? Okay. So 6 says, in which diagram of a current carrying solenoid is the magnetic field correctly represented? So they all look good in terms of, well, the magnetic field lines make that oval shape. You know, they all have like the appropriate shape there. So what's the difference? These are going out of the left into the right. So are these. But these are going out of the right into the left. These are also going out of the left into the right. And let's take a look. What else is different? This is negative on the left, negative on the left, positive on the left, positive on the left. So there's some differences here. The first thing I would do is draw the direction of, oh, and what else is different? The wires in front on the right, in front on the left, in front on the left, and in front on the right. That's another difference that we have to look at. That's important. That's going to show what direction our fingers should be wrapping, and that'll determine what direction our thumb is pointing. And we want the arrows coming out of our thumb, okay, and into the other side of our hand. So first, let's draw the direction of the current. For A, the current goes out of positive into negative, so the current is going here. Same for C. I guess let's go to B. Out of positive into negative, out of positive into negative. For C, out of positive into negative. And for D, is going out of the positive side into the negative side. So that's going to show us what direction to wrap our fingers around the thing. So the next thing we should be looking at is where is the wire? So for A, the wire is in front on this side. So I'm going to like put my pencil horizontally, and I'm going to wrap my fingers in front of it. You should be looking at the back of your hand right now. And your thumb should be, if you're using your right hand, your thumb should be pointing to the left. Make sure you're using your right hand. That's the one on the right. So your fingers are wrapping in front of it, and your thumb is pointing to the left. So I don't know. Yeah, if my thumb's pointed to the left, that means north is here and south is here. So this one's looking good. Are we going to get the same thing for B? Now let's look at B. Okay, is B correct? Well, I'm looking at the left-hand side. My fingers are again wrapping in front, so it's the same scenario as before. My thumb is on the left-hand side, so my thumb is here. But the arrows, these magnetic field lines, are pointing in to north. No, they don't point into the north side. They're supposed to point out of the north side. So we know B is no good because those magnetic field lines are the opposite of what they should be. For C, now it's wrapping behind. So over here is where I'm looking right now. Okay, the wire goes behind the rod. So you're going to put your fingers behind your pencil. You should be looking like you're at the palm of your hand, and your thumb is pointing to the right. So we like flipped it from before. We're using our right hand, and our thumb is pointing to the right now. And that means if our thumb is pointing to the right, north is here. And again, those magnetic field lines are pointing into north. No, we want them to go out of north into south. So that's no good. One more. So it goes, again, your thumb is oriented to the right because your fingers are wrapping behind the rod, behind your pencil, and your thumb points to the right. So that's where north is. But the magnetic field lines are, again, pointing into the north, so that's no good. So that's why choice A is the correct one. Man, that's some tricky stuff. Ready for it to get harder? This is number 7. This is, I know right away we're starting with right hand rule number 3 because there's a pre-existing magnetic field, and then there's going to be another magnetic field because of this moving charge. So if there's a pre-existing magnetic field, you know we're going to be doing right hand rule number 3. So it's number 7. All right, so it says the diagram below shows electron E about to enter the region between the poles of the two magnets. Upon entering the region between the poles, the moving electron will experience a magnetic force directed where? So where's the force pointing? So there's 3 different things that we're looking at. We have a pre-existing magnetic field flowing out of north into south. So we need to put our magnetic field, that's the B, our middle finger is pointing down. Our middle finger is pointing down. The electron is moving to the right, so that means conventional current is pointing this way, and our index finger is where the conventional current points. So if our middle finger is pointing down, everybody point on your right hand, point your middle finger down, and then like you have to make your index finger 90 degrees to that, and point your index finger to the left, because that's where conventional current's going, opposite the electron flow. What direction is your thumb pointing? It has to be pointing towards you. Your thumb should be pointing right at you, out of the page. So we know the force being felt is out of the page. It's going to be a dot out of the page. So it says, upon entering the region between the poles, the moving electron will experience a magnetic force directed out of the page. Some tricky stuff. All right, again, your thumb, see how like it's this way? This is the direction that we wanted. This should be rotated down because this is pointing down. And if you rotate your hand like that, if you make this go down, see how the thumb is rotating 90 degrees towards you? Now your thumb is pointing at you. All right. Okay. So again, out of north into south. That's the direction of your middle finger, the magnetic field. So everybody point your middle finger to the right. You might have to like move your hand. It's going to be a little uncomfortable maybe. All right, but your right hand, the middle finger has to be pointing to the right. The current in the wire, so it says it's carrying conventional current as denoted by X. So now move your pointer finger, your index finger, this one. We have our middle finger pointing to the right. And you have to rotate your hand. See, it's kind of fun. It's like trying to figure out what to do with your hand. It's weird. Your index finger is pointing into the page, into the screen. So your middle finger is pointing to the right. Your index finger is pointing into the screen. What direction is your thumb? Your thumb should be pointing down towards C. You guys doing this at home? Are you following along? There's some tricky stuff. All right, number 9. In the diagram below, a free electron is traveling upward at speed v parallel to a conductor. Oh my God. An electron current begins to flow upward in the conductor, meaning the conventional current is flowing downward. Oh boy. And then it's saying which diagram best represents the resulting magnetic field, B, and the direction of the magnetic force, F, on the free electron. This is the last question, and it's the last question for the reason. It's a doozy. Is this right hand rule number 1 or right hand rule number 3? It's both. First, you have to figure out what direction is this correct or not? Then, once you know what direction the magnetic field should be pointing, then you could start looking at this and it's like, is the force pointing in the right direction? Okay. So there's going to be two different currents, and they're both flipped because they're electron and electron, but we want where the conventional current is going. Oh man, what a confusing question. It's fun though. Try to figure it out. It's like so different from what we normally do with calculations and graphs. This is none of that. It's like a completely out of left field thing. So try to figure it out. I'm not going to do it. No, I'm just kidding. I'll do it. So electron current is pointing up in the wire. Let's start there. I'm going to start drawing. Boom. Really, they mean I is pointing down. And this is going to help us with right hand rule number 1. So we're going back to where our thumb points in the direction of the current. So it's going to look opposite from what this hand looks like because it's a thumbs down for this question. Anybody else give this question a thumbs down? No, it's a fun one. See how all the conventional currents are pointing down? So put your thumb down. You got to do it. If you're not doing it with your hand, then you're not going to understand this. All right, so you got to point your thumb down. What direction are your fingers wrapping around? Like if you hold your pencil, and then now we're looking at these arrows. Which of these arrows closely represent where your fingers are wrapping? Is it A and B, or is it C and D? All right, so hopefully you said my thumb is down, I'm wrapping my fingers around there. C and D is looking good to me, and these are wrong. Nope. Okay, so I guess let's erase this, and then let's do the right hand rule number 3 now that we know what direction the magnetic field is pointing. Okay, so let's get these options out of there. We don't want those. All right, let's zoom in on these two. So these two, so far, we said, okay, according to right hand rule number 1, the magnetic field is correct for C and D. So now that we know what direction the magnetic field is and where this electron is, the field goes, okay, it's going around here, and then it's over here. So that means the field is going out of the page over here. So it's like a dot. Okay, so the magnetic field is pointing out of the page. What direction and by the way, so now we're looking at right hand rule number 3. Okay, and we have the magnetic field, that is this one here, is pointing out of the page. Ooh, so far this diagram is similar to what we're doing, but we're going to rotate. This is going to be a different direction. So we're going to rotate our index finger. What direction should our index finger be? Should it be up or down? Let's take a look. So the electron is flowing upward. Conventional current goes opposite electron flow. So this is where conventional current is going. So we want our index finger to be pointing downward. And we want our middle finger, this is B for the direction of the magnetic field. The dot means out of the page. So can you point down, point downward, stick your middle finger out. Don't flip me off. All right, pointing downward. Make your middle finger 90 degrees to your index finger, just like it is in this diagram here. Everybody see where I'm going with this? You're pointing downward, middle finger out, but your middle finger is pointing towards you. You're really going to have to move your arm around. Index finger down, middle finger towards you. What direction is your thumb pointing? What? Where is it pointing? The thumb shows the direction of the force. That's where the thumb is. So if your index finger is pointing down for the current, and your middle finger is pointing out towards you, it's pointing out of the page towards you. Your thumb should be pointing towards the left. Your thumb should be pointing towards the left. And that's why this is the correct answer. Choice D. Wow. Right hand rules. Everybody loves them. But actually, only physics teachers do. No. Hopefully you had some fun doing it. And don't worry too much about it because it's probably not going to be on the New York State Regents exam. Have a great day.